It's 4 a.m. and I can't sleep. Not because I'm anxious. Not because I drank too much coffee, though I did, the mug still warm in my hand. Third refill tonight. I can't sleep because I keep thinking about my keys. They're sitting on the desk, right there, maybe 30 centimeters from my hand. I can see them, chrome glinting under the desk lamp. The little keychain my niece made me, faded blue thread wrapped around a wooden bead. 30 centimeters. But here's what's keeping me awake. Those 30 centimeters aren't just distance, they're also time. If I want to grab those keys, I have to move my hand through space, yes, but I also have to move through time. Takes what? Half a second? A second if I'm being lazy about it. And I can't separate those two things. I can't grab the keys without time passing. I can't let time pass without my hand moving through space. Space and time are tangled together in a way that feels obvious when you think about it, but also completely wrong. Because we don't experience them the same way, do we? Space feels solid, three-dimensional. I can move forward, backward, left, right, up, down. I have choices. I can grab the keys or not grab the keys. I can walk to the window or stay at the desk. But time just happens. One direction. Forward. Always forward. I can't go back to yesterday. I can't skip ahead to next week. Time drags me along whether I want it to or not. So how can they be the same thing? Einstein said they are. He said space and time are woven together into a single fabric. Space-time. Not two separate things, but one unified structure that bends and warps and curves. And sitting here at 4 a.m. staring at my keys, I'm trying to understand what that actually means. Not the equations. I know the equations. I've taught the equations. But what does it mean? What does it feel like to live in a universe where space and time are the same thing? That's what keeps me up at night. That's what we're going to explore. The keys are still sitting there. I've been staring at them for, 10 minutes? 20? Time gets weird when you're this tired. The coffee's gone cold in my hand. 4th cup tonight. Or is it 5th? There's a ring of dried coffee on the desk from where I set the mug down earlier and forgot about it. The keys are maybe 30 centimeters away. Chrome glinting under the desk lamp. That little blue keychain my niece made me last year. The thread's starting to fray now. I can see every detail. The scratches on the metal, the way the light catches the ridges. 30 centimeters. I could reach out and grab them right now. Just extend my arm, close my fingers, done. Half a second of movement. But here's the thing that's keeping me awake. I can't separate those two measurements. 30 centimeters of space, half a second of time. They're not two different things. They're the same thing described in different units. And that should be obvious, right? Of course it takes time to move through space. Of course. But it's not obvious. Not really. Because we don't experience space and time the same way at all. Space feels negotiable. I can move left or right, forward or backward. I can reach for the keys or not reach for them. I have options. Freedom. 3 dimensions of possibility. Time just happens. One direction. Forward. Always forward. I can't go back to yesterday. I can't pause this moment and stay in it. Time drags me along whether I want it to or not. So how can they be the same thing? That's what I'm trying to figure out. That's why I'm still sitting here at 4 a.m., staring at my keys, drinking cold coffee, thinking about Einstein. Let me show you what I mean. What does it mean to say the keys are 30 centimeters away? It means there are 30 centimeters of space between my hand and the keys. 30 centimeters of what? Air? Electromagnetic field? Gravitational field? All of the above? Let's say I want to measure that distance. How do I do it? I could use a ruler. Press one end against my hand, stretch it out to the keys, read the number. 30 centimeters. Done. But what's the ruler actually measuring? It's measuring how many times its own length fits into the gap. The ruler is, let's say, 30 centimeters long. I put it between my hand and the keys, and it fits exactly once. Therefore, the distance is 30 centimeters. But how do I know the ruler is 30 centimeters long? Because someone measured it against a standard meter stick. And how was that meter stick measured? Against another standard. and so on, all the way back to the official definition of the meter, which, as of 1983, is defined as the distance light travels in 1,299,792,458th of a second. Wait, the definition of distance is based on time. The meter, the fundamental unit of space, is defined by how far light travels in a specific amount of time. Space and time are already tangled together in the definition. We can't even define one without the other. Let's talk about light for a minute. Light travels at 299,792,458 meters per second in a vacuum, always, no matter what. This is one of the strangest facts in physics, and we've gotten so used to it that we forget how weird it is. Here's why it's weird. Speed is distance divided by time. If I drive 100 kilometers in 1 hour, my speed is 100 kilometers per h. Simple, but speed is relative, right? If I'm on a train moving at 100 kilometers per h, and I walk forward at 5 kilometers per h, then relative to the ground, I'm moving at 105 kilometers per h. Speeds add, except for light. If I'm on a spaceship moving at half the speed of light, and I shine a flashlight forward, how fast is the light moving? You'd think half the speed of light from the ship plus the speed of light from the flashlight equals 1.5 times the speed of light. But no, the light is still moving at exactly the speed of light, 299,792,458 meters per second. Not faster, not slower. This doesn't make sense. It violates our intuition about how speeds should add. But it's true. We've measured it. Over and over. Light always travels at the same speed, regardless of how fast the source is moving. And this fact, this one weird, stubborn fact, breaks our understanding of space and time. Here's why. If the speed of light is constant, and speed is distance divided by time, then distance and time can't both be constant. Let me say that again, slower. Speed equals distance/time. If speed is always the same and I change how fast I'm moving, then either distance or time or both has to change to keep the equation balanced. And that's exactly what happens. When you move faster, distances contract. Time dilates. Space and time warp to keep the speed of light constant. This is Einstein's special relativity. And it's not a theory in the sense of a guess. It's a theory in the sense of a mathematical framework that makes predictions. And every single prediction has been confirmed by experiment. GPS satellites have to account for this. Particle accelerators have to account for this. If we didn't understand relativity, your phone's map wouldn't work. Space and time are flexible. They bend. They stretch. They're not the rigid absolute stage that Newton thought they were. And they're not independent. They're coupled, linked, woven together. Let me give you a thought experiment. Imagine you're standing still and I'm on a spaceship flying past you at, let's say, 80% the speed of light. From your perspective, I'm moving very fast. Time on my spaceship is passing slower than time for you. If I have a clock and you have a clock, my clock is ticking slower. But from my perspective, I'm not moving. You're moving. You're flying past me at 80% the speed of light in the opposite direction. So from my perspective, your clock is ticking slower. We both see the other person's time moving slower, and we're both right. How is that possible? Because there's no absolute time. There's no universal clock ticking away in the background, keeping track of the time. Time is local, personal. It depends on your reference frame. And the same is true for space. From your perspective, my spaceship is contracted in the direction of motion. It's shorter than it was when it was at rest. From my perspective, you're contracted, you're shorter. Again, we're both right. Space and time are not absolute. They're relative. They depend on the observer. And the only thing that's absolute, the only thing that everyone agrees on regardless of how fast they're moving, is the speed of light. I'm looking at the keys again. They're still 30 centimeters away. But now I'm thinking, 30 centimeters in whose reference frame? If I were moving very fast relative to the desk, the distance would be different. Space would contract, the keys would be closer. And if I were moving very fast, time would dilate. The half second it takes to reach for them would stretch out or compress depending on who's watching. Distance and duration are not fixed. They're not properties of the universe. They're properties of the relationship between me and the keys. Space and time are relational. Here's another way to think about it. You can't measure distance without time. Even with a ruler, you're implicitly using time. The ruler is made of atoms, and atoms are held together by electromagnetic forces which propagate at the speed of light. The length of the ruler is determined by how far light can travel in the time it takes for forces to balance. And you definitely can't measure distance with light without time. Radar works by sending a signal and measuring how long it takes to bounce back. Distance equals speed times time. You need time to measure space. Similarly, you can't measure time without space. Clocks work by counting oscillations, a pendulum swinging back and forth, a quartz crystal vibrating, a cesium atom transitioning between energy states. All of these involve movement through space. The pendulum swings through space. The crystal vibrates in space. The electron in the cesium atom moves through space. Time is measured by motion through space. Space and time are not separate. They're two aspects of the same thing. Let me tell you about something that happened to me a few years ago. I was teaching an intro physics class, and we were talking about the speed of light. One of the students, bright kid, always asking good questions, raised his hand and said, "If light takes time to travel, does that mean we're always seeing the past?" And I said yes, absolutely. Light from the lamp takes a few nanoseconds to reach your eyes. Light from the sun takes 8 minutes. Light from the nearest star takes 4 years. When you look at the night sky, you're looking at the past. Some of those stars might not even exist anymore. They might have exploded, died, vanished. But their light is still traveling through space, and we're seeing them as they were, not as they are. The student thought about this for a moment, then said, "So there's no such thing as now for the whole universe. Now is different depending on where you are." And I just stood there, a little stunned, because that's exactly right. There is no universal now. There's no moment that's the present for everyone, everywhere. Now is local. It's here. It's the intersection of your world line with this particular slice of space-time. Someone on Mars has a different now. Someone in another galaxy has a different now. And if there's no universal now, then the distinction between past, present, and future starts to blur. But that's a thought for later. We'll get there. Right now, I want to come back to the room, the desk, the lamp, the keys. I've been talking about relativity and light speed and reference frames, but let me bring it back to something concrete. The space between my hand and the keys is not empty. It's full of fields, electromagnetic fields, gravitational fields, maybe even fields we haven't discovered yet. And those fields have structure, they have geometry. When I move my hand through that space, I'm not moving through nothingness. I'm moving through a structured medium. The fields are interacting with the atoms in my hand, pushing and pulling, guiding the motion. And that motion takes time. Not because time is some separate thing that happens alongside the motion, but because motion through space is motion through time. They're the same thing. Here's a way to visualize it. Imagine a graph. The horizontal axis is space. The vertical axis is time. Every event, every moment, every location is a point on this graph. Me sitting at the desk right now, 1 point. Me reaching for the keys a second from now, another point. The path between those 2 points is called a world line. It's the trajectory of my hand through space-time, not through space, then through time. Through space-time, a single, unified, four-dimensional structure. And the length of that world line, the distance between the two events, is measured in a unit that combines space and time. Physicists call it the space-time interval. It's a bit like the Pythagorean theorem, but with a twist. Instead of distance squared equals x squared plus y squared, it's interval squared equals time squared minus space squared. Notice the minus sign, that's important. It means space and time contribute differently to the interval. They're not quite the same, but they're not separate either. They're woven together, inseparable. I think the hardest part of understanding this is letting go of the idea that space and time are fundamentally different. We experience them differently. That's undeniable. Space feels like a place. Time feels like a flow. But our experience is not a reliable guide to reality. We experience the Earth as flat, but it's round. We experience solid objects as continuous, but they're mostly empty space with tiny atoms scattered around. We experience colors as inherent properties of objects, but they're just wavelengths of light interpreted by our brains. Our intuition is built for survival, not for understanding the universe. And when we look closely, when we measure carefully, when we do the experiments, we find that space and time are not what they seem. They're not separate. They're not absolute. They're not a stage on which events happen. They're part of the events themselves. The keys are still there. I still haven't grabbed them. But now, when I look at them, I see something different. I see 30 centimeters of space, yes, but I also see half a second of time. And I see the electromagnetic field between us, carrying the light that lets me see them. And I see the gravitational field curving the space around the Earth, holding everything in place. I see a structure, a geometry, a fabric, and I'm part of that fabric. My hand, my body, my thoughts, they're all patterns in space-time, moving along world lines, tracing paths through a four-dimensional continuum. The distance between me and the keys is not just a gap to be crossed, it's a relationship, a connection, a piece of the geometry of reality. It's almost 5 a.m. now. The sky outside is starting to lighten. Not sunrise yet, but that deep blue that comes before dawn. The city lights are fading. I can hear birds starting to sing. I should probably get some sleep. But I won't. Not yet. Because I'm thinking about time now. About how it flows, or seems to flow. About how it's different from space even though they're the same thing. Space feels static. Time feels dynamic. But is that real? Or is that just how we experience it? What if time doesn't actually flow? What if the flow is an illusion, a trick of consciousness, a side effect of how our brains process information? What if all of time, past, present, future, exists simultaneously, laid out like a landscape, and we're just moving through it, experiencing one moment at a time? That's the next question. But first, I need more coffee. The keys can wait. The clock on the wall is analog, old-fashioned, round face, white background, black numbers, second hand sweeping around in that smooth, continuous motion. Tick, tick, tick. I inherited it from my grandfather. He was a watchmaker, spent his whole life taking apart tiny mechanisms, cleaning gears, adjusting springs. He used to say that time was the only thing you couldn't fix once it was broken. I didn't understand what he meant back then. I think I'm starting to now. The clock says 5:17 a.m., each second passing with metronomic precision, steady, reliable, absolute. Except it's not absolute. That's the thing Einstein figured out. Time is not a universal constant ticking away in the background of the universe. Time is local, personal. It depends on where you are and how fast you're moving. The clock on my wall is ticking at a different rate than a clock on a spaceship, than a clock on top of a mountain, than a clock falling into a black hole. Time bends. Time stretches. Time can even stop. And once you understand that, really understand it, the whole universe starts to look different. Let me tell you about Einstein's dream. Not a metaphor. An actual dream he had when he was 16 years old. He dreamed he was riding on a beam of light, traveling through space at 299,792,458 meters per second. And he asked himself, what would I see? If light is a wave and I'm traveling alongside it at the same speed, would the wave appear frozen? Would I see a stationary pattern of electric and magnetic fields suspended in space like a sculpture? This question bothered him for years. It didn't make sense. Maxwell's equations, the laws of electromagnetism, don't allow for stationary light waves. Light has to move. That's what it is. Movement. But if you're moving at the speed of light, how can light still be moving relative to you? The answer Einstein eventually arrived at is this. You can't travel at the speed of light. Not you can't because we don't have the technology. You can't because the universe won't let you. As you approach the speed of light, time slows down. From your perspective, everything is normal. But from an outside observer's perspective, your clock is ticking slower and slower. And if you could reach the speed of light, which you can't, but if you could, time would stop completely. You would be frozen, not in space, in time. Every photon of light that has ever existed experiences zero time. From the photon's perspective, if photons had perspectives, it is emitted and absorbed in the same instant. No duration, no passage, just existence at 2 points in space, with no time in between. Light doesn't experience time. And that's not poetic language, that's physics. I'm trying to imagine what that would feel like, not moving through time, just existing, all at once, no before, no after, just now, stretched across space. But I can't imagine it. My brain doesn't work that way. I'm built to experience time sequentially, one moment after another. Cause, then effect, memory, then anticipation. The flow of time feels so fundamental to my experience that imagining its absence is like imagining not existing at all. But the flow is not fundamental. It's not built into the universe. It's built into me. Let's talk about the twin paradox. It's not really a paradox. It's just deeply weird. Imagine two twins. Let's call them Alice and Bob. They're both 20 years old. Alice stays on Earth. Bob gets on a spaceship and travels to a star 10 light years away at 90% the speed of light. Then he turns around and comes back at the same speed. From Earth's perspective, the trip takes about 22 years. Alice is now 42 years old. But from Bob's perspective, time has been passing slower. Not because of anything biological, because of relativity. Time itself has been dilated. When Bob gets back, he's only aged about 10 years. He's 30 years old. Alice is 42. Bob is 30. They're twins, but Alice is now 12 years older than Bob. This is not science fiction. This is real. This is what the equations predict, and the equations have been tested over and over. Muons, subatomic particles created in the upper atmosphere, live longer when they're moving fast. Atomic clocks on airplanes tick slower than atomic clocks on the ground. GPS satellites have to account for time dilation, or your phone's map would be off by kilometers. Time is not absolute. It's relative. It depends on your velocity. But here's the part that messes with my head. From Bob's perspective, he's not the one moving. Alice is. Bob is sitting in his spaceship, perfectly still relative to himself. It's Earth that's moving away from him at 90% the speed of light, then moving back toward him. So from Bob's perspective, shouldn't Alice's time be the one that's dilated? Shouldn't Alice be the younger one when they reunite? This is the paradox part. Both twins see the other one moving. Both should see the other one's time slowing down. But when they meet up again, only one of them has aged less. So who's right? The answer is, Bob is the one who accelerated. Alice stayed in one inertial reference frame the whole time. She didn't speed up or slow down. She just sat on Earth, orbiting the sun, moving at a constant velocity. Bob, on the other hand, had to accelerate to get up to speed, then decelerate to turn around, then accelerate again to come back. An acceleration breaks the symmetry. When you accelerate, you're changing reference frames. You're moving from one slice of space-time to another, and that changes which events are simultaneous for you. It's hard to visualize. I've been teaching this for years, and I still have to draw diagrams to keep it straight. But the math is clear. Bob ages less. Alice ages more. Time is not the same for both of them. Now let's make it weirder. Gravity also slows time. Not just velocity. Gravity. The stronger the gravitational field, the slower time passes. If you're standing at the bottom of a mountain, time is passing slightly slower for you than for someone standing at the top. The difference is tiny, nanoseconds per day, but it's real. We've measured it. If you're standing on the surface of a neutron star, a star so dense that a teaspoon of it would weigh 1 billion tons, time is passing much slower for you than for someone far away in empty space. And if you're at the event horizon of a black hole, the point of no return where gravity is so strong that not even light can escape, time nearly stops. From your perspective, falling into a black hole, everything seems normal. You cross the event horizon, you keep falling, you eventually hit the singularity at the center. But from the perspective of someone watching you from far away, you never cross the event horizon. You get slower and slower as you approach it. Your clock ticks slower, your movements become sluggish. You freeze, asymptotically approaching the horizon but never quite reaching it. You're stuck there, frozen in time, forever. Except you're not, because from your perspective, you've already fallen in. Both perspectives are correct. Time is relative. I need to pause here and say something. This is not intuitive. This is not how we experience the world. And that's okay. Intuition is built from experience, and our experience is limited to slow speeds and weak gravity. We've never traveled at 90% the speed of light. We've never stood on a neutron star. So our brains didn't evolve to understand relativity. They evolved to understand thrown rocks and running prey, and whether that shadow in the bushes is a predator. But the universe doesn't care about our intuition. The universe follows rules, and those rules are mathematical, and the math says that time is flexible. And once you accept that, once you let go of the idea that time is absolute, you start to see the universe as it really is. Not a stage with a universal clock ticking in the background, but a dynamic, interconnected structure where time is woven into space, where past and future are relative concepts, where now is local and personal. Here's a thought experiment I like to use in class. Imagine you're standing on Earth and your friend is on Mars. You both agree to clap your hands at exactly noon, Earth time. From your perspective, you clap at noon. Your friend claps at noon. You're synchronized. But now imagine a spaceship flying past Earth toward Mars at half the speed of light. From the spaceship's perspective, the two claps are not simultaneous. Because of the way relativity works, the spaceship sees your friend on Mars clapping before you clap on Earth. The order of events is different depending on who's watching. Now, this only works for events that are space-like separated, events that are far enough apart in space and close enough in time that light couldn't travel between them. If one event causes another event, if there's a causal connection, then everyone agrees on the order, because always comes before effect. But for events that don't influence each other, that are separated by too much space and too little time, the order is relative. Your now is not the same as someone else's now. There is no universal present moment. Let me bring this back to the clock on the wall. It's 5:34 now. 17 minutes have passed since I started writing this section. But 17 minutes according to whom? According to the clock on the wall, which is sitting here in my lab, at rest relative to Earth, in Earth's gravitational field. If I had a clock on a GPS satellite, it would show a different time. The satellite is moving fast relative to Earth, and it's higher up, weaker gravity. Both effects change the rate at which time passes. The satellite's clock ticks faster than my clock by about 38 microseconds per day. That doesn't sound like much. But GPS works by measuring the time it takes for signals to travel from satellites to your phone. If the clocks were off by 38 microseconds per day, your position would be off by kilometers within a week. So GPS satellites have to correct for relativity. They have to slow down their clocks to match Earth time. Every time you use your phone's map, you're relying on Einstein's equations. Time dilation is not abstract. It's not theoretical. It's built into the technology we use every day. There's something deeply unsettling about all this. We like to think of time as a river. We're floating along, carried by the current, moving from past to future at a steady rate. But relativity says there is no river. Or rather, everyone has their own river, flowing at their own rate. My river is not your river. My now is not your now. And if we're moving at different speeds or in different gravitational fields, our rivers are flowing at different rates. We're all experiencing time, but we're not experiencing the same time. Here's a question that keeps me up at night. If time is relative, if there's no universal now, then what is time? Is it a dimension? Like space? Is it a property of the universe? Is it something that exists independently? Or is it just a way we organize our experiences? I don't have a good answer. The best answer I have is this. Time is what clocks measure. That sounds like a cop-out, but it's actually profound. A clock is any system that undergoes regular periodic change, a pendulum swinging, a quartz crystal vibrating, a cesium atom transitioning between energy states. Time is the counting of those changes. And because different clocks can tick at different rates, because time dilates with velocity and gravity, time is not a single universal thing. It's a collection of local measurements. Each clock measures its own time, and those measurements don't always agree. My grandfather's clock is still ticking. Tick, tick, tick. Each tick is a moment, a slice of time, a heartbeat of the universe. But whose universe? The clock's universe, the local universe. The universe as experienced by an object at rest in this lab, on this planet, in this gravitational field. If I took the clock to the top of a mountain, it would tick faster. If I took it on a spaceship, it would tick slower. The clock doesn't measure some abstract universal time. It measures the time along its own path through space-time, its own world line. And every object has its own world line, its own path, its own time. There's a phrase I love, proper time. Proper time is the time measured by a clock that's moving along with you. It's your personal time, the time you experience. If you're sitting still, your proper time is just regular time, 1 second per second. But if you're moving fast, or in a strong gravitational field, your proper time is different from the proper time of someone else. And here's the beautiful part. Proper time is invariant. That means everyone agrees on it. If your clock ticks 10 times, everyone agrees that your clock ticked 10 times, even if they disagree on how much time passed for them. Proper time is the one thing that's absolute in relativity. It's the length of your world line through space-time. Everything else, distance, duration, simultaneity, is relative. But proper time is real. I think this is why time feels so different from space. Space feels negotiable. I can move left or right. I can choose my path. But time feels inevitable. I can't choose to go backward. I can't choose to stop. And that's because I'm always moving through time at the speed of light. Wait, let me explain that. In space-time, you're always moving. Even if you're sitting perfectly still in space, you're still moving through time. And the faster you move through space, the slower you move through time. Your total velocity through space-time is always the same, the speed of light. If you're sitting still in space, all of your motion is through time. You're aging at the maximum rate. If you're moving through space at half the speed of light, some of your motion is through space, so less of it is through time. You're aging slower. If you could move through space at the speed of light, all of your motion would be through space, and none of it would be through time. You wouldn't age at all. This is why light doesn't experience time. It's moving through space at the speed of light, so it has no motion left over for time. I'm staring at the clock again, 5:51 a.m. The second hand is sweeping around, smooth, continuous, inexorable, but now I see it differently. I see it as a marker, a pointer, indicating my position along my world line. I'm moving through space-time at the speed of light. Always, constantly. I can't stop. I can't slow down. But I can change direction. If I start moving through space, if I get up from this chair and walk across the room, some of my motion through time gets redirected into motion through space. I age a tiny bit slower, not enough to notice, not even close, but it's real. Every step I take through space is a step I'm not taking through time. Here's the thing that really gets me. We think of time as something that happens to us. We're passive, time flows, and we're carried along. But that's not quite right. We're not passive. We're moving, actively, through space-time, and the path we take, the world line we trace, is determined by our choices. If I reach for the keys, I'm choosing a path through space-time that brings me closer to them. If I stay sitting here, I'm choosing a different path. Both paths are real. Both are possible. And the path I choose determines my proper time, my aging, my experience. Time is not something that happens to me. It's something I move through. The sky outside is lighter now. Not quite sunrise, but close. That pale grey blue that comes just before the sun breaks the horizon. I can see the outline of buildings, the trees, the street below. The world is waking up. And I'm still here, thinking about time. About how it bends, how it stretches, how it's not the same for everyone. About how my grandfather's clock is ticking away, measuring time that's local and personal and real, but not universal. About how every second that passes is a step along my world line, a movement through space-time, a choice about how to allocate my motion between space and time. Time is not a river. Time is a dimension, a direction, a component of the fabric of reality, and we're all moving through it at our own rates, along our own paths. But if time is a dimension, if it's woven into space, if past and future are just directions like left and right, then what is the fabric itself? What is space-time really? Not the metaphor, not the analogy, the actual thing. That's the next question. But first, I need to watch the sunrise. Some things are worth experiencing in real time, even if real time is relative. Not dramatically, not like in the movies where golden light floods the room and everything becomes clear. Just up, a pale disk behind the morning haze. The sky is that washed-out blue-grey that means it's going to be overcast later. I should probably open the window, get some fresh air. The lab smells like old coffee and dust, and the faint electrical smell of equipment that's been running all night. But I don't want to move yet, because I'm thinking about fabric, not literal fabric, not cotton or silk or whatever my shirt is made of, but the fabric of space-time, the thing Einstein said space and time are woven into. And I'm trying to figure out what that actually means, because fabric is a metaphor, right? It's a way of visualizing something that's fundamentally invisible and abstract. Space and time aren't literally made of threads. There's no cosmic loom weaving reality. But the metaphor keeps coming up because it's useful. It helps us think about how space-time can bend and stretch and curve. Except, what does it mean for something to bend if it's not embedded in something else? That's the part that always trips me up. Let me start with the classic analogy. You've probably seen it. A rubber sheet stretched flat, representing space-time. You place a heavy ball in the middle, representing the sun or earth or any massive object, and the sheet sags. It curves downward, creating a depression. Now you roll a smaller ball across the sheet. Instead of traveling in a straight line, it curves toward the depression. It orbits the heavy ball. This is gravity. Not a force pulling the small ball toward the big ball, but the curvature of space-time guiding its motion. It's a beautiful analogy. I use it in class all the time, but it's also deeply misleading, because the rubber sheet is curving downward. Down relative to what? Relative to a third dimension, the vertical dimension that the sheet is embedded in. But space-time isn't embedded in anything. There's no higher dimension that it's curving into. Space-time curves into itself. And that's where the analogy breaks down. That's where you have to let go of visualization and trust the math. Here's what I mean. Imagine you're an ant living on the surface of a sphere, a balloon, let's say. You can walk forward, backward, left, right, 2 dimensions. That's your entire universe. Now, from outside the balloon, we can see that the surface is curved. It's a 2-dimensional surface embedded in 3-dimensional space. But you, the ant, don't see that. You don't have access to the third dimension. You can't step off the balloon and look at it from the outside. All you can see is the surface. And from your perspective, the surface looks flat, locally anyway. But if you walk in a straight line long enough, you'll eventually come back to where you started. And that's weird. That's not what happens on a flat plane. So you can infer from the geometry of your universe that it's curved, even though you can't see the curvature directly. That's what space-time is like. We're embedded in it. We can't step outside and look at it from a higher dimension. But we can measure its geometry. We can see how light bends, how clocks slow down, how orbits precess. And from those measurements we can infer that space-time is curved, not curved into something, just curved. This is hard to wrap your head around. I've been studying this for years and I still don't have a good intuitive grasp of it. But the math is clear. Space-time is a 4-dimensional manifold, 3 dimensions of space, 1 of time. And the geometry of that manifold is described by something called the metric tensor. The metric tensor tells you how to measure distances and durations in space-time. It tells you how much space there is between 2 points and how much time elapses between 2 events. And in the presence of mass or energy, the metric tensor changes. Space-time curves. This is Einstein's general relativity. The equations are beautiful and terrifying. 10 coupled nonlinear partial differential equations that describe how matter and energy warp the geometry of space-time. I'm not going to write them out here. You don't need to see the equations to understand the idea. The idea is this. Mass and energy tell spacetime how to curve. Spacetime tells matter how to move. It's a feedback loop, a dance. Matter curves spacetime, and curved spacetime guides matter. Let me give you a concrete example. The Earth orbits the Sun. Why? Newton would say, because the Sun's gravity pulls on the Earth. Einstein would say, because the Sun's mass curves space-time, and the Earth is following the straightest possible path through that curved space-time. Wait, straightest path? But the Earth's orbit is curved. It's an ellipse. Yes, in space the orbit is curved, but in space-time, it's straight. Let me explain. Imagine you're looking at a map, a flat map of the Earth. You want to fly from New York to Tokyo. On the map, the shortest path looks like a straight line heading west. But if you actually fly that route, you'll notice something weird. The plane doesn't fly west the whole time. It flies northwest, then southwest. Why? Because the Earth is a sphere, and the map is a flat projection of that sphere. The straight line on the map is not actually the shortest path on the sphere. The shortest path on a sphere is called a great circle. It's the path you get if you stretch a string tight between 2 points on the surface. And on a flat map, great circles look curved. The same thing happens in space-time. The Earth is following the straightest possible path through space-time. But because space-time is curved by the Sun's mass, that straight path looks curved when we project it onto space. The Earth isn't being pulled by a force, it's just moving freely through curved geometry. This is what Einstein meant when he said gravity is not a force, it's geometry. There's a word for these straightest possible paths, geodesics. On a flat surface, a geodesic is a straight line. On a curved surface, a geodesic is, well, it depends on the curvature. On a sphere, geodesics are great circles. In space-time curved by the Sun, geodesics are elliptical orbits. And here's the beautiful part. Everything follows geodesics. Always, unless there's a force acting on it. If you're floating in space far from any planets or stars, you're following a geodesic, a straight line through flat space-time. If you're orbiting the Earth, you're following a geodesic, a curved path through curved space-time. If you're sitting in a chair right now, you're not following a geodesic. The chair is pushing up on you, exerting a force preventing you from following the natural curvature of space-time. In fact, you can feel that force right now. It's the feeling of weight, the pressure of the chair against your body. That's not gravity, that's the chair pushing you off your geodesic. Gravity is what you feel when there's nothing pushing you. When you're in freefall, when you're following the curvature of space-time. This is one of the most counterintuitive ideas in physics. We think of gravity as a force pulling us down. But really, the ground is pushing us up. If the ground weren't there, we'd fall. We'd follow our geodesic. We'd accelerate toward the center of the Earth at 9.8 meters per second squared. Not because something is pulling us, but because space-time is curved, and our natural path through that curved space-time is downward. The ground interrupts that path. It exerts a force. It pushes us off our geodesic. And we feel that force as weight.
Okay, deep breath.
I know this is a lot. I know it's weird. But stay with me because it gets weirder. If space-time is curved by mass and energy, and if we're all moving through space-time along geodesics, then there's a question we need to ask. What happens when space-time is really curved? Not just a little bit, like near the Earth or the Sun, but a lot? What happens near a black hole? A black hole is what you get when you compress enough mass into a small enough space that the curvature of space-time becomes extreme. The exact threshold is called the Schwarzschild radius. For the Earth, it's about 9 millimeters. If you could compress the entire Earth into a sphere 9 millimeters across, it would become a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with the mass of 1,000,000 suns, the kind that sits at the center of most galaxies, the Schwarzschild radius is about 3 million kilometers. At the Schwarzschild radius, something strange happens. Spacetime curves so much that the geodesics, the straightest possible paths, all point inward. There is no outward path, no sideways path. Every direction leads toward the center. This is the event horizon, the point of no return. If you cross the event horizon, you can't come back. Not because something is pulling you in, but because every possible path through spacetime leads inward. Even light can't escape. not because it's not fast enough, but because there's no outward direction to travel in. I'm trying to visualize this and failing. The rubber sheet analogy doesn't work here. You can't make a rubber sheet curve so much that all directions point inward, but the math works. The equations are clear. Inside the event horizon, the roles of space and time swap. Outside the event horizon, you can move through space in any direction, but you're forced to move forward in time. Inside the event horizon, you can move through time in any direction, past or future, but you're forced to move inward in space. The singularity at the center of the black hole is not a place. It's a moment, a point in time, not space. And you're falling toward it the same way you're falling toward next Tuesday. Inevitably. Inexorably. This is what I mean when I say space-time is not a metaphor. It's not a convenient way of talking about space and time as if they were connected. They are connected. They are the same thing. And the geometry of that thing can be so extreme that the rules change, that space becomes time, and time becomes space. The fabric is real. Let me come back to something more familiar. Light. Light always travels along geodesics. Always. It has no choice. In flat space-time, far from any massive objects, light travels in straight lines. But in curved space-time, light's path curves. This is gravitational lensing. Light from a distant star passes near the sun, and the sun's mass curves space-time, and the light follows that curvature, bending slightly. We've measured this. During a solar eclipse in 1919, astronomers observed stars near the sun and found that their positions were shifted exactly as Einstein's equations predicted. It was one of the first confirmations of general relativity, and it's not just a small effect. When light from a very distant galaxy passes near a massive cluster of galaxies, the curvature can be so strong that we see multiple images of the same galaxy distorted and stretched into arcs. The galaxy's light is following multiple geodesics through the curved space-time around the cluster, and we see all of them. It's beautiful, and it's proof that space-time is not just an abstract concept. It's a physical thing with measurable properties. Here's another way to think about it. Every event in space-time has a light cone. Imagine you're standing here, right now, this moment, this location. This is an event in space-time. Now imagine all the possible paths that light could take from this event. Light spreading outward in all directions at 299,792,458 meters per second. In 1 second, that light forms a sphere, 1 light second in radius. In 2 seconds, a sphere, 2 light seconds in radius. And so on. If you plot this in space-time, with time as the vertical axis and space as the horizontal axis, you get a cone. The light cone. Everything inside the cone is in your future. You can influence it. You can send signals to it. You can travel to it. Everything outside the cone is not in your future. You can't influence it. You can't send signals to it. You can't travel to it. Because that would require traveling faster than light. And you can't travel faster than light because light defines the structure of space-time. The light cone is not just a visualization. It's a fundamental feature of reality. Causality, the idea that causes precede effects, is built into the geometry of space-time. If event A is in the past light cone of event B, then A can influence B. If event A is outside the light cone of event B, then A cannot influence B. This is why faster-than-light travel would break causality. If you could travel faster than light, you could send a signal outside your light cone. You could influence events that are space-like separated from you, and depending on your reference frame, that could look like sending a signal backward in time. You could, in principle, send a message to your past self. You could create a paradox. The universe doesn't allow this, not because of some cosmic rule against paradoxes, but because the geometry of space-time doesn't permit it. Faster-than-light travel is not just technologically impossible, it's geometrically impossible. I'm looking out the window now. The city is waking up. Cars on the street below. People walking to work. The coffee shop on the corner is open. Lights on, steam rising from the espresso machine. All of this, every person, every car, every photon of light, is moving through space-time along geodesics. The cars are following curved paths because the Earth's mass curves space-time. The people are being pushed off their geodesics by the ground beneath their feet. The light from the coffee shop is travelling in straight lines through the nearly flat space-time of the city, and I'm sitting here, motionless in space, moving through time at 1 second per second, tracing my world line through the four-dimensional manifold that is reality. There's something profound about this. We think of space as empty, as nothing, as the stage on which events happen. But space is not empty. Space is not nothing. Space is part of space-time, and space-time has geometry, and that geometry is dynamic. It bends and stretches and curves in response to matter and energy. And we're not separate from it. We're embedded in it. We're made of it. Every atom in my body is a pattern in space-time. Every thought in my brain is a process unfolding along a world line. I am not in space-time. I am space-time, a localized, temporary, self-aware pattern in the fabric of reality. The coffee's gone cold again. I should make a fresh pot. Or maybe I should just go to the coffee shop downstairs, get some actual food, talk to another human being. But I'm not done yet. Because there's still a question I haven't answered. If space-time is a fabric, if it has geometry, if it can bend and curve and stretch, then why does it only bend in one direction? Why does time have an arrow? Why do we remember the past but not the future? Why do eggs scramble but not unscramble? Why does entropy always increase? The geometry of space-time doesn't prefer one direction over another. The equations of general relativity work the same forward and backward in time. So where does the arrow come from? That's the next question. But first, I really need more coffee. I made it to the coffee shop. Barely. My legs feel like they're made of wet cardboard. That's what happens when you stay up all night thinking about space-time. The barista, her name tag says Maya, gives me a look that's half concern, half amusement. Rough night? Long night, I say. Physics. She nods like that explains everything. Maybe it does. I order a double espresso and a croissant. The croissant is warm, flaky, smells like butter and yeast. I can't remember the last time I ate. I take the coffee and pastry to a table by the window and sit down. The chair is real, solid, the coffee is hot, the croissant is perfect. And I'm thinking about eggs. Here's a simple fact. If you drop an egg, it breaks. The shell cracks. The yolk spills out. The white spreads across the floor in a sticky puddle. You've seen this happen. Everyone has. Now here's a question. Have you ever seen the reverse? Have you ever seen a broken egg spontaneously reassemble itself? The puddle of white flowing back together, the yolk reforming, the shell pieces flying up from the floor and fusing back into a smooth, unbroken surface? No, of course not. That doesn't happen. But why not? Think about it. The laws of physics are time-symmetric. If you film a planet orbiting the sun and play the video backward, it still looks like a planet orbiting the sun. The equations of motion work the same in both directions. If you film 2 billiard balls colliding and play it backward, it still looks like 2 billiard balls colliding. Conservation of momentum works the same forward and backward. But if you film an egg breaking and play it backward, you immediately know something's wrong. Broken eggs don't unbreak. Spilled milk doesn't unspill. Shattered glass doesn't unshatter. There's a direction to time, an arrow, a preferred way that events unfold. And that arrow is not in the fundamental laws of physics. It's somewhere else. The answer is entropy. Entropy is a measure of disorder, of randomness, of the number of ways a system can be arranged. A whole egg has low entropy. There's only one way, roughly speaking, to arrange the molecules so that you have an intact egg. A broken egg has high entropy. There are countless ways to arrange the molecules so that you have a puddle of yolk and whitened shell fragments. And the second law of thermodynamics says entropy always increases. In a closed system, over time, things get more disordered, more random, more spread out. This is why eggs break but don't unbreak. This is why coffee cools down but doesn't spontaneously heat up. This is why your room gets messy but doesn't spontaneously clean itself. Entropy increases, always, and that increase gives time a direction. But here's the weird part. The second law of thermodynamics is not a fundamental law. It's a statistical law. What does that mean? It means it's not impossible for a broken egg to reassemble itself. It's just incredibly, stupendously, astronomically unlikely. Let me explain. Imagine you have a box with a partition in the middle. On one side you have 100 gas molecules, on the other side, nothing, vacuum. Now you remove the partition. What happens? The gas molecules spread out. They fill the entire box. They distribute themselves evenly, more or less, across the available space. This is entropy increasing. The molecules were ordered all on one side, and now they're disordered, spread throughout the box. But here's the thing. The molecules are just bouncing around randomly. They're following Newton's laws of motion, and Newton's laws are time-symmetric. So, in principle, the molecules could, by pure chance, all end up back on one side of the box. It's not forbidden by the laws of physics. It's just incredibly unlikely. How unlikely? Well, each molecule has a 50% chance of being on the left side at any given moment. For all 100 molecules to be on the left side simultaneously, the probability is 100 circumflex 100. That's about 1 in 10 circumflex 30, 1 in a million trillion trillion trillion. If you waited for the age of the universe, 13.8 billion years, you still wouldn't see it happen. But it's not impossible, just unlikely. This is the key insight. The second law of thermodynamics is not a law in the same sense that Newton's laws are laws. It's a statistical tendency, a statement about probabilities. In a system with many particles, there are vastly more disordered states than ordered states. So if you start in an ordered state and let the system evolve randomly, it will almost certainly end up in a disordered state. Not because there's a law forcing it to, but because there are more ways to be disordered than to be ordered. Entropy increases because disorder is more probable than order. I take a bite of the croissant. It's delicious, buttery, crisp on the outside, soft on the inside. And it's a highly ordered structure, layers of dough and butter, carefully folded and baked, low entropy. If I leave it sitting here long enough, it will decay. The butter will oxidize, the dough will dry out, bacteria will colonize it, it will crumble into dust, entropy will increase, and I will never, ever see that dust spontaneously reassemble itself into a fresh croissant. Not because it's impossible, but because it's so unlikely that I could wait for a trillion universes to live and die and it still wouldn't happen.
Okay, so entropy increases because disorder is more probable than order.
But that raises a question. If entropy always increases, then it must have been lower in the past. And if you go back far enough, it must have been very low, extremely low, impossibly low. And that's exactly what we find. The Big Bang. 13.8 billion years ago, the universe began in a state of extremely low entropy. All the matter and energy in the universe was compressed into an incredibly small, incredibly hot, incredibly dense point. And that point was highly ordered. I know that sounds wrong. How can something hot and dense and chaotic be ordered? But remember, entropy is not about how messy something looks. It's about the number of possible arrangements. In the early universe, all the matter and energy was in a very specific configuration. There were very few ways to arrange it. As the universe expanded and cooled, that matter and energy spread out. It formed atoms, then stars, then galaxies. It became more complex, more varied, more disordered. Entropy increased, and it's been increasing ever since. This is the origin of time's arrow. The universe started in a low entropy state, and entropy has been increasing ever since. We remember the past because the past was lower entropy. Our brains store memories by creating ordered structures, neural connections, chemical gradients. That requires entropy to increase elsewhere in the form of heat, waste products, etc. We can't remember the future because the future is higher entropy. There's no ordered structure in the future that we can access from the present. The arrow of time is the arrow of entropy. But this raises a deeper question. Why did the universe start in a low entropy state? Why wasn't the Big Bang just a random high entropy mess? This is one of the biggest unsolved problems in physics. We don't know. Some physicists think it's just a brute fact. The universe started that way, and that's that. Others think there's a deeper explanation. Maybe the Big Bang wasn't the beginning. Maybe it was a transition from a previous state. Maybe there's a multiverse. And our universe is just one bubble in a vast foam of universes, and we happen to be in a bubble that started with low entropy. I don't know. Nobody knows. But what we do know is this. The low entropy of the early universe is the reason we experience time as flowing from past to future. It's the reason we age. It's the reason we remember yesterday but not tomorrow. It's the reason eggs break but don't unbreak. The arrow of time is not built into the laws of physics. It's built into the initial conditions of the universe. I'm watching the steam rise from my coffee. The coffee is hot. The air is cool. Heat is flowing from the coffee to the air, warming the air, cooling the coffee. Entropy is increasing. The molecules in the coffee are moving fast, vibrating, colliding. The molecules in the air are moving slower. When they collide with the coffee molecules, energy is transferred. The fast molecules slow down. The slow molecules speed up. Eventually, the coffee and the air will reach the same temperature, thermal equilibrium. And at that point, entropy will be maximized. There will be no more heat flow, no more change. This is the heat death of the universe. If the universe keeps expanding forever, eventually all the stars will burn out, all the black holes will evaporate, all the matter will decay into radiation, and the universe will reach a state of maximum entropy. A cold, dark, uniform soup of particles, all at the same temperature, with no structure, no complexity, no life. Nothing will happen anymore. Not because time stops, but because there's no entropy gradient left to drive change. The arrow of time will still exist, technically, but it won't point anywhere interesting. This is depressing. I don't like thinking about the heat death of the universe. But it's also kind of beautiful in a bleak way. Because it means that right now, this moment, this cup of coffee, this croissant, this conversation with Maya the barista, is part of a temporary island of order in a universe that's slowly dissolving into chaos. We exist because the universe is out of equilibrium. Because entropy is increasing, but hasn't finished increasing yet. We're riding the wave of entropy, surfing the gradient between the low entropy past and the high entropy future. And when the wave flattens out, when entropy reaches its maximum, we'll be gone, but not yet, not for a long, long time. Let me come back to something more immediate. Why do we perceive time as flowing? I've been talking about entropy and the arrow of time, but I haven't really addressed the feeling of time passing, the sense that the present moment is special, that the past is fixed and the future is open, that we're moving through time from one moment to the next. Is that real, or is it an illusion? Here's one way to think about it. Imagine a movie, a film reel with thousands of frames, each one a still image. When you watch the movie, you see motion. You see characters moving, talking, living, but the motion is an illusion. The film is static. All the frames exist simultaneously. The motion is created by your brain, which processes the frames sequentially and interprets the differences between them as movement. Maybe time is like that. Maybe all of time, past, present, future, exists simultaneously, like frames in a film. And maybe our perception of time flowing is just our consciousness processing those frames sequentially. Each moment of your life is a frame, and your brain, moving from one frame to the next, creates the illusion of flow. This is called the block universe view. The idea is that space-time is a four-dimensional block, with all of time laid out like a landscape. Your birth is one point in the block, your death is another point, and every moment of your life in between is also a point. All of those points exist, right now, simultaneously. There's no objective now, no universal present moment, just different slices of the block experienced by different observers. And the flow of time, the feeling that the present is moving from past to future, is not a feature of the universe. It's a feature of consciousness. I'm not sure I believe this. It feels wrong. It feels like the present moment is real in a way that the past and future are not. The past is gone. The future hasn't happened yet. Only the present exists. But that's not what relativity says. Relativity says there's no universal present. Different observers have different nows. And if there's no universal present, then the distinction between past, present, and future is not fundamental. It's observer-dependent, subjective. Maybe the flow of time is subjective too. Here's another thought: memory. We remember the past because our brains store information about past events, neural connections, chemical changes, physical structures that encode what happened, but those structures exist in the present. the past itself is gone. All we have is present moment evidence of the past, and we don't have present moment evidence of the future. We can't remember tomorrow because tomorrow hasn't created any structures in our brains yet. So the asymmetry between past and future, the fact that we remember one but not the other, is not about time itself. It's about entropy. Memory requires low entropy initial conditions and high entropy final states. You start with an ordered brain, you experience an event, and you create a memory by increasing entropy, generating heat, using energy, etc. You can't create memories of the future because that would require decreasing entropy, and entropy doesn't decrease. So the arrow of time, the direction from past to future, is the same as the arrow of entropy. They're not two different things. They're the same thing viewed from different angles. The coffee is lukewarm now. I should have drunk it faster. Entropy wins again. I take a sip anyway. It's not great, but it's caffeine, and I need caffeine. Maya is wiping down the counter, humming to herself. A couple of other people have come in. A guy with a laptop, a woman with a book. The morning crowd. Everyone here is a temporary island of order, a low-entropy structure maintained by constant input of energy, food, oxygen, sunlight indirectly. We're all fighting entropy, eating, breathing, metabolizing, repairing cellular damage, and we're all losing. Slowly, inevitably. Entropy always wins in the end, but not today. There's something I find comforting about this. The fact that we exist at all is a kind of miracle, not a supernatural miracle, a statistical miracle. The universe started in a low-entropy state for reasons we don't understand, and that low-entropy state allowed for the formation of stars, planets, chemistry, life, consciousness. We're here because the universe is out of equilibrium, because there's an entropy gradient, because time has an arrow, and that arrow is pointing from the ordered past to the disordered future. We're surfing that arrow, riding the wave of increasing entropy. And the wave will eventually crash. The universe will reach maximum entropy. Everything will stop. But right now, the wave is still rising, and we're still here. I finished the croissant. It's gone now. Converted into energy, into heat, into the chemical processes that keep me alive. Entropy has increased. And I'm okay with that, because that's what life is. A temporary decrease in local entropy, paid for by a larger increase in entropy elsewhere. We are entropy's children, born from disorder, sustained by disorder, destined to return to disorder. But in the meantime, we get to experience this. The taste of coffee, the warmth of the sun, the sound of Maya humming, the feeling of being alive. And that's enough. I'm thinking about the block universe again. If all of time exists simultaneously, then this moment, right now, me sitting in this coffee shop, drinking lukewarm coffee, thinking about entropy, is eternal. It's not passing. It's not disappearing into the past. It's just here. A point in space-time, a frame in the film. And every other moment of my life is also here, also eternal. My childhood, my first day of school, the day my grandfather gave me his clock, the night I stayed up late reading about relativity for the first time. All of it exists. All of it is real, not in the past, in space-time. And if that's true, then nothing is ever really lost. The past is not gone. It's just elsewhere. Another slice of the block. I don't know if I find that comforting or terrifying, both maybe, but it's making me think, if the block universe is real, if all of time exists simultaneously, then what does that mean for free will? For choice? For the feeling that the future is open and the past is fixed? That's the next question. But I think I need a nap first, or at least another coffee. I didn't get a nap. I got another coffee instead, double shot. Maya raised an eyebrow but didn't say anything. Now I'm back in the lab. It's almost noon. The sun is high, pale behind the clouds. The room is warmer than it was at 4 a.m. The dust motes are visible in the light from the window, drifting slowly, following air currents I can't see. The keys are still on the desk. I still haven't grabbed them, and I'm thinking about something that's been bothering me since I started this whole line of thought. If space and time are the same thing, if they're woven together into a four-dimensional fabric, if there's no universal now, then when is now? Let me put it differently. Right now I'm sitting at my desk. It's 11:47 a.m., January 9th, 2026. That's now for me. But what about someone on Mars? What's now for them? You might say, the same time. 11:47 a.m., January 9th, 2026. But that's not quite right. Because of the distance between Earth and Mars and the finite speed of light, there's no way to synchronize clocks perfectly. What I call now on Mars depends on my reference frame. If I'm sitting still relative to the Sun, then now on Mars is one thing. If I'm moving toward Mars at high speed, then now on Mars is something else. The events that are simultaneous with this moment, the events that are happening now, depend on how I'm moving. There is no objective, universal now. This is called the relativity of simultaneity. And it's one of the strangest consequences of special relativity. Here's a thought experiment to illustrate it. Imagine a train moving past a platform at high speed. There's a person on the train, let's call her Alice, and a person on the platform, let's call him Bob. At the exact moment Alice passes Bob, two lightning bolts strike the train, one at the front, one at the back. From Bob's perspective, standing on the platform, the two lightning bolts strike simultaneously. He sees the flashes at the same time after accounting for the time it takes light to reach him. But from Alice's perspective, on the moving train, the lightning bolts do not strike simultaneously. Because Alice is moving toward the front of the train, the light from the front lightning bolt reaches her before the light from the back lightning bolt. And since the speed of light is the same in all reference frames, Alice concludes that the front lightning bolt struck first. Bob says they struck simultaneously. Alice says the front one struck first. They're both right. Simultaneity is relative. Now extend this to the entire universe. Every event in space-time has a now, a set of events that are simultaneous with it, from some observer's perspective. But different observers have different nows, and if there's no universal now, then the distinction between past, present, and future is not absolute. It's observer-dependent. From my perspective, sitting here at my desk, some events are in my past, some are in my future, and some are happening now. But from a different perspective, someone moving at a different velocity, the boundaries between past, present, and future are drawn differently. Events that are in my future might be in their past. Events that are in my past might be in their future. This leads to a strange conclusion. If there's no universal now, then all of time, past, present, future, must exist in some sense. Not will exist or did exist, just exists. This is the block universe. The idea is that space-time is a four-dimensional block, with all of time laid out like a landscape. Every event that has ever happened, is happening or will happen, exists as a point in this block. Your birth, your death, this moment, right now, reading these words. All of it exists simultaneously, not in time, in space-time. I'm trying to wrap my head around this. It feels wrong. It feels like the present moment is special, like it's the only moment that's real. The past is gone. It's over. It doesn't exist anymore. The future hasn't happened yet. It doesn't exist either. Only the present exists. Right? But relativity says no. Relativity says the present is not special. It's just a slice through space-time, and different observers slice it differently. And if the present is not special, then the past and future are just as real as the present. They're just elsewhere, other slices of the block. Let me try to visualize this. Imagine a loaf of bread. The loaf is space-time. Four-dimensional, but we'll pretend it's three-dimensional so we can picture it. Each slice of bread is a moment in time, a three-dimensional snapshot of the universe at a particular instant. When you slice the loaf straight across, you get one set of slices. These are the now slices for an observer at rest. But if you slice the loaf at an angle, you get a different set of slices. These are the now slices for an observer in motion. The loaf itself doesn't change. It's the same loaf. But the way you slice it depends on your reference frame. And all the slices exist. They're all part of the loaf. This is the block universe. Your entire life from birth to death is a path through the loaf, a world line. And that world line exists. All of it. Right now. Not right now in the sense of the present moment, but right now in the sense of space-time. In the eternal, timeless sense, every moment of your life is a point on that world line. And all those points exist simultaneously. I don't like this. I don't like the idea that my future is already laid out. That every choice I'll ever make has already been made in some sense. It feels like it takes away my agency, my freedom. If the future already exists, then how can I change it? How can I make choices? This is the free will problem, and it's been debated by philosophers for centuries. If the universe is deterministic, if the future is determined by the past and the laws of physics, then do we have free will? Or are we just following a script that was written at the Big Bang? I don't have a good answer, but I have some thoughts. First thought, determinism and free will might not be incompatible. This is called compatibilism. The idea is that free will doesn't require the ability to have done otherwise. It just requires that your choices are your own, that they come from your desires, your beliefs, your reasoning. Even if those desires and beliefs are determined by prior causes, they're still yours. And the choices you make based on them are still free in the sense that they're not coerced by external forces. You're following your world line through space-time, but that world line is shaped by who you are, by your thoughts, your values, your decisions. The future is determined, but it's determined by you. Second thought, maybe the block universe doesn't mean the future is determined. Maybe it just means the future exists, without specifying what it is. This is harder to explain. But think about it this way. The block universe says that all of space-time exists. But it doesn't say that there's only one possible space-time. Maybe there are multiple possible futures, multiple possible world lines, and the one you end up on depends on your choices. The block universe would then be the set of all possible space-times, not a single fixed space-time. This is speculative. I'm not sure it makes sense, but it's a way of reconciling the block universe with the feeling that the future is open. Third thought, maybe the feeling of free will is an illusion, and that's okay. Maybe we don't actually have the ability to choose otherwise. Maybe our choices are determined by the laws of physics and the initial conditions of the universe. But we still experience the feeling of making choices. We still deliberate, weigh options, decide. And that experience is real, even if the outcome was determined. The illusion of free will is good enough for practical purposes. I'm not satisfied with any of these answers, but I don't think there is a satisfying answer. The free will problem is one of those questions that philosophy and physics can't fully resolve. We can describe how the universe works. We can map out the structure of space-time. We can write down the equations. But we can't tell you what it feels like to be a conscious agent moving through that space-time, making choices, experiencing the flow of time. That's something you have to figure out for yourself. Let me come back to the block universe. If all of time exists simultaneously, then the past is not gone. It's still there, still real, just in a different part of space-time. Every moment of your childhood, every conversation you've ever had, every mistake, every triumph, every mundane Tuesday afternoon, all of it exists, not in memory, in space-time. And the same is true for the future. Every moment you'll ever experience, every choice you'll ever make, every person you'll ever meet, all of it exists, right now, in the block. This should be terrifying. The idea that my entire life is already laid out, that I'm just moving through a predetermined path, that there's no real freedom or spontaneity. But I don't find it terrifying. I find it comforting, almost, because it means that nothing is ever truly lost. The past is not gone. It's eternal. Every moment I've ever lived is still there, still real, still part of the structure of space-time, and the future is not uncertain. It's already there, waiting for me to experience it. I'm not creating the future. I'm discovering it. Of course, from my perspective, inside the block it doesn't feel like that. It feels like the present is moving, like time is flowing, like I'm making choices and shaping the future. And maybe that's the point. Maybe the block universe is the view from outside, the God's eye view, the perspective of someone who can see all of space-time at once. But I'm not outside. I'm inside. I'm embedded in the block. And from inside, time flows. The present feels special. The future feels open. Both perspectives are true. They're just different ways of looking at the same thing. I'm looking at the keys again. They've been sitting there for 8 hours now. In the block universe, there's a world line for those keys, a path through space-time that includes every moment of their existence. The moment they were manufactured, the moment my niece attached the blue keychain, the moment I set them on the desk last night, this moment, right now, where they're sitting there, glinting in the afternoon light, and every future moment, the moment I'll eventually grab them, the moment I'll use them to unlock my car, the moment they'll get lost or broken or thrown away. All of those moments exist. All of them are real, and my world line intersects with their world line at various points. Right now is one of those points. I reach out and grab the keys. The metal is cool in my hand. The blue thread of the keychain is soft, frayed at the edges. I've been thinking about this simple action for 8 hours, 30 centimeters of space, half a second of time. But now I understand it differently. I didn't move through space and then through time. I moved through space-time, along a geodesic, a path determined by the curvature of space-time around the Earth, by the electromagnetic forces between the atoms in my hand and the atoms in the keys, by the choices I made, or didn't make, depending on your view of free will. The movement was inevitable, not because it was predetermined, but because it was part of the structure of space-time. It was always going to happen. It's happening right now. It will always have happened. Past, present, and future, all woven together. There's a phrase I keep coming back to, eternalism. The view that all moments in time are equally real, that the past and future exist in the same way the present does. It's the opposite of presentism, which says that only the present exists. I think I'm an eternalist. Not because I've proven it, not because I have some knockdown argument, but because it fits with relativity. It fits with the idea that space-time is a four-dimensional structure, that there's no universal now, that time is just another dimension. And it fits with my experience, in a strange way, because even though I experience time as flowing, even though the present feels special, I also have this sense that the past is still real. My memories are not just representations of things that used to exist, they're connections to moments that still exist in space-time. And the future is not just a blank slate, it's a landscape I'm moving toward, a part of space-time I haven't experienced yet, but that's already there. I set the keys back down on the desk. I don't need them right now. But I know they'll be there when I do, not because they're sitting in one place in space, waiting for time to pass, but because their world line and my world line intersect at multiple points in space-time, and one of those points is in my future. It's almost 1 p.m. now. I've been awake for more than 24 hours. My eyes are burning. My thoughts are getting fuzzy. I should really get some sleep. But I'm not tired, not in the way that makes you want to stop. I'm tired in the way that makes everything feel a little unreal, a little dreamlike. The lab, the desk, the keys, the dust motes drifting in the sunlight. All of it feels like it's part of something larger, something eternal. A four-dimensional structure that contains every moment that has ever been or ever will be. And I'm a part of that structure, a pattern in space-time, a world line stretching from my birth to my death, with every moment of my life laid out along it. I think about my grandfather. He died 10 years ago, but in the block universe, he's still there, still real. Not in the past, in some abstract sense. In space-time, every moment of his life, working in his shop, repairing watches, teaching me about gears and springs, still exists. I can't visit those moments. I can't go back in time. But they're there, eternal, unchanging. And in some sense, he's still there too, still alive in those moments. Not alive in the present, but alive in space-time. This is what I find comforting about the block universe. It means that nothing is ever truly lost. Every moment you've ever experienced, every person you've ever loved, every place you've ever been, it's all still there, not in memory, not in the past, in space-time. And it will always be there, because space-time doesn't change. It just is. I'm looking out the window now. The city is going about its day, cars moving through streets, people walking on sidewalks, birds flying overhead. All of them are world lines, paths through space-time. And all of those paths exist. All of them are real. the car that just drove past. Its world line includes every moment of its existence. The factory where it was built, the dealership where it was sold, this moment driving down the street, the junkyard where it will eventually be scrapped. All of it exists. All of it is real, and the same is true for me. My world line includes my birth, my childhood, this moment sitting at my desk, and my death. All of it exists. All of it is real. I'm not moving from the past to the future. I'm not creating the future as I go. I'm discovering it, experiencing it, one moment at a time. But here's the thing. Even though the block universe says that all of time exists, it doesn't say that time doesn't flow. It just says that the flow is subjective, personal, a feature of consciousness, not a feature of space-time. And that's okay, because the flow is real to me. The present feels special. The future feels open, and that experience is valid, even if it's not fundamental to the structure of reality. I think about the question I started with. Are space and time the same thing? And the answer is yes and no. Yes, in the sense that they're both dimensions of space-time. They're woven together into a single structure. You can't have one without the other. No, in the sense that we experience them differently. Space feels static. Time feels dynamic. But that difference is not in the universe. It's in us. We're embedded in space-time, moving along world lines, experiencing one moment at a time. And from that perspective, time flows. The present is special. The future is open. But from the perspective of space-time itself, the God's eye view, the view from outside, there is no flow. There is no present. There is just the block, eternal and unchanging. Both perspectives are true. The keys are still on the desk. I'm still in the lab. The sun is still shining through the window, and I'm still here, thinking about space-time, about entropy, about the nature of reality. I should probably get some sleep, but I think I'll stay up a little longer. Because this moment, right now, sitting here, thinking these thoughts, is part of my world line. It exists in space-time. It's eternal, and I want to experience it fully before I move on to the next moment, and the next, and the next. Space and time are the same thing. They're dimensions of a four-dimensional structure that contains everything that has ever happened or ever will happen. We move through that structure along world lines, experiencing one moment at a time, feeling the flow of time even though the flow is not fundamental. And that's beautiful, because it means we're part of something larger, something eternal. We're patterns in space-time. Temporary, yes, but also eternal, in the sense that every moment we experience is forever part of the structure of reality. We are space-time, experiencing itself, one moment at a time. I close my eyes, just for a moment, and I feel it, the flow of time, the movement from one moment to the next. It's not an illusion, it's real. But it's also not fundamental. It's the way space-time feels from the inside. And that's enough.